Okay, so here is, excuse me, Unit 2 of Electricity and Magnetism for AP Physics C. It is titled Conductors, Capacitors, and Dielectrics. So if you're interested in computers, these are capacitors that are on motherboards. That's the reason why we have a motherboard sitting behind us. Okay, so what we're going to do right now is we're going to begin talking, or so this first section is going to focus around conductors, but what we're going to do is I'm going to split this up into three separate videos, and that's because if we do it as one video, it's going to end up being probably about 30 minutes long. So I want to give you guys a little sanity and break it up into only a handful, into three videos. Okay, so here in the first video, we're going to look at like what is a conductor, what is the electric field in conductor, and how do we determine the potential difference on a conductor, right? Because these are some of the basic things that you do need to know and understand for the AP Physics C exam. And these are very important because you have to pay attention to how the question is worded, because they may talk insulator, they may say conductor, and so if it's an insulator, you have to treat it differently as a conductor. Okay, so let's first talk about conductors and E fields and potentials inside conductors. So the first thing is a conductor, right, is a material that has free electrons that are allowed to move freely. Okay, so they can shift around as much as they want, right? But they're going to do something special to make it very helpful for us in doing some calculations. Okay, what are good conductors? Well, metals. Right. This is why you don't want to stick anything metal into a light socket because it's a great conductor of electricity and as well as of heat. And the reason why is because of these free electrons. Right. These are the ones that are allowed to move around. Okay. And with metals, they want that electron, that those electrons are going to move very, very easily. Okay. Now, if there's any excess charge on an isolated conductor, it's going to spread along the surface of the conductor until there is no more movement of the charge. Okay. And so if we quickly look down at this little, so here is a conducting sphere. And so we have all this excess charge, right, running around on the inside. And what it's going to do, it's going to move, right, until it's sitting on the surface, right? And then they're going to space themselves out because this is now a special condition that we call electrostatic equilibrium. Now, on that diagram, I'm only showing a handful of charges, but understand this is like I don't know, we're talking Avogadro's numbers, right, worth of electrons that are of particles that are excuse me, that are going to shift around, okay, onto this surface. Now, with that being said, right, for an arbitrarily shaped conductor carrying excess charge, when it is in equilibrium, right, when it's in this electrostatic equilibrium, there are certain things that are going to happen, right? So any excess charge will reside entirely on the surface of the conductor, right? And so remember, if this is a neutral object and all of a sudden it's charged, well, the net charge is still going to essentially be zero, right? And what's happening is all that excess charge that is floating around there is going to sit on the surface. Okay. Now, the electric field inside the conductor is zero, right? And this is the big one, right? And so, anytime it says a conducting sphere, a conducting piece of metal, a conducting this, a conducting that, and it talks about the inside of that sphere, piece of metal, the electric field inside will be zero, right? And here's the reason why. If the field was not zero, the charge inside the conductor will accelerate, right? Because now you're going to have a net force, right? Or it would be accelerating, right? So the charges will redistribute themselves wherever they are needed to make the field inside the conductor zero, right? So these are going to, as I did before, these are going to kind of move around and say, okay, I want to move here, I want to move there, right? Because I want that inside, the Q inside is going to be zero. All right, now the electric potential will be constant, right, inside the conductor, and it's equal to the potential at the surface, right? And so that's just telling us that whatever the electric potential is, so whatever voltage is given to this conductor, it's the same throughout. Okay, and again, right, if there was a potential difference, that means you would have charges kind of flowing around in there. Okay. So this is what we call an equipotential surface. Equi, make sure I spell this right. Potential surface, right? And you see the key kind of start to this equi, right? That means equal. So that means this is the potential on that surface will always be the same. All right. And then the outside, right? The electric field just outside the surface of the conductor is perpendicular to the surface. Perpendicular, right? This is also another word that I always have to make sure I spell it right. Um, Now, the magnitude of the electric field is going to be equal to E equals sigma over epsilon naught, right? And we've talked about that sigma before when we were talking about electrostatics in unit one. Okay. And that's just in general, right? So whatever the E field is going to be that charge density, that local surface charge density over epsilon naught, right? Now, spheres, we can treat them like point charges. So we know how to calculate the E field. We know how to calculate the potential, right? The E field is just going to be given by our KQ over R squared equation. And remember that Q, right? If you need to, is going to be that surface charge density, right? Because they may give you, so sigma is charge over area. So that would make Q sigma times area, right? So just be aware they may give you something strange like that. Um, and then the um, potential is just going to give given by KQ over R. All right. Now, here's something that the AP test may look at or ask you questions about is the electric field and electric potential graphs. And so, what do they look like on for a conductor, right? And so, if this is my E versus R, right? So my electric potential versus R, where we're starting at zero, which is the center of the um, of the sphere, right? And so inside a conducting sphere, the electric potential will be zero, right? And once you get outside that surface, then it follows this KQ over R squared. So it would do something like that. Okay. Now, if you, so that is our E versus R, electric field versus distance graph. And now, if we look at our potential, our electric potential, we said that it's going to, inside to the surface is going to be all equal. All right. And so if capital R is the radius of our point charge, that means the for inside the conductor, it's going to be constant. Right. And if you remember, um, to go from V or get V from E, you're going to take the integral, right? The integral of zero is a constant value. Okay. And then we have our now this is varied by 1 over R squared, and this one varies by 1 over R. I apologize if they look very similar, but just understand you have to remember that we're going to the potential graph will start at the whatever the voltage is and drop from there. Okay, so um, now for irregular shaped conductors where there's no symmetry, right? So something that may look like, if you have a conductor that looks like this, okay, one thing, the field will not be symmetrical, which means it's not the same at all points on the surface, right? And then so the again though, because this is a conducting object, the E field will still be zero, and you'll still have all this excess charge kind of sitting on top, right? But what you'll notice that is because there's perpendicular to this, right? If you look like here, you're gonna have all this stuff kind of like all mashing together, right? And so sometimes it may cancel out, sometimes it may build, right? Um, so the electric potential everywhere inside the conductor again is equal, right? Again, like anytime you talk about conductor, E field is always zero, right? Potential electric potential is always equal to whatever the potential is. Okay. Now the field, so the field is greatest at places where the surface curves the most. And why does that happen? Is because of this perpendicularness, right? And as I mentioned, there may be times where the field may cancel out, right? Because it's like equal but opposite. But there are also times where it's going to build, right? Because you're going to have more of that, more concentration of the E field sitting in that position. So I'd have more concentration here than I would have here. So my E field would be bigger, than, at that point where you got all this stuff kind of grouped together, and then you do when it's not so grouped together. Okay. And so remember, in static equilibrium, or I probably should say in electrostatic equilibrium, right? The electric field must be perpendicular. Keep using that word because you have to hold true to that. And if the field was not perpendicular, there would be a force on the free electrons causing them to accelerate. Okay, so this will end the first video. So part one of conductors, of like, if you want to say unit 2.1, okay, is focusing around conductors. In the next video, we're going to look at how do we calculate the electric potential, and we're going to look at some different look at some problems for that.